Greetings of the day, students. Welcome to the new session of COALP. In last lecture, we have started the control unit, in which we have taken the overview of hardwired control unit and microprogrammed control unit. Right. So in today's lecture, we will be covering these two topics in detail, and we will be discussing some new topics also. So in last lecture, we have discussed that a control unit is made up of hardwired control unit is made up of sequential and combinational circuits to generate the control signals, right? Whereas microprogrammed control unit, a control memory on the processor contains the microprograms that activate the necessary control signals. So in hardwired organization, control logic is implemented with gates, flip-flops, decoders, and other digital circuits. So it has the advantage that it can be optimized to produce a fast mode of operation. So it requires changing in the wiring among the various components if the design has to be modified or changed, right? So because in hardwired organization, we don't have any microprogram present, right? That is the reason you need to change the wiring among the various components if you need to change some design or you need to do some modification. So this is the basic diagram for hardwired control unit, in which we have used two decoders, 3 into 8, whose size is 3 into 8, and the second one decoder is 4 into 16, right? One IR means instruction register, some logic gates, which is called combinational control logic, and a sequence counter, right? So we have used a total 4 components. I'm repeating again. It consists of 2 decoders, a sequence counter, a number of control logic gates, right? So an instruction read from the memory is placed in the instruction register. First of all, whenever the instruction which is read from the memory, it will be placed into the instruction register, which is of 16 bits, right? So you can see the bifurcation of IR. So 0 to 11 bits represents the address. It will be fed into the combinational control logic. Then the operation code, which will be depicted with the help of bit number 12, 13, and 14, right? It will be given as an input to 3 into 8, right? So 3 inputs, number 1, number 2, and number 3. 3 into 8, and 8 outputs will be taken out from this 3 into 8 decoder, right? Let me explain. First of all, an instruction which is read from the memory, it will be placed into the instruction register. Right, your 16-bit instruction will be placed into this IR. IR is a register which is of 16 bits. That is why I have represented it with 0 to 15 bits. Right. After that, this 0 to 11 bits, it represents your address, if you remember. So it will be given as an input to combinational logic gates, where we have a combination of multiple gates and core, node, XOR. All the combinational gates will be placed over here, right? After that, the 3 inputs, that is bit number 12, 13, and 14, which is represented with operation code, right? It will be fed as an input to 3 into 8 decoders, 3 inputs, 8 outputs, right? So 0 to 7, right? So again, this bit 0 will be represented with D note, D1, D2, 1. This is bit number 1, 2, 3, 4, 5, 6, which will be represented with D note, D1, D2, and so on up to D7. D means decoded, because it will be taken out from the decoder. That is why it will be represented with D note, D1, D2, D3, and so on. Right? I hope the concept is clear to you. Right? So again, it will be given as an input to your combinational logic gate. Right? After that, one more decoder is used whose size is 4 into 16, which will take 4 inputs and give you 16 outputs. Right? So that is why this is called 4 into 16 decoder, which means 4 inputs are there and 16 outputs are there. In the same way as in earlier, 3 into 8, 3 inputs are there and 8 outputs will be there. Right? So inputs are your separation code, bit number 12, 13, and 14. Right? Which will be converted to 8 outputs, D note to D7, right? 8 outputs. Then we have 4 inputs will be given to this decoder, 4 into 16. These 4 inputs will be taken from the SC. SC stands for sequence counter. SC stands for sequence counter. Its value is keep on incremented by 1. Sequence counter is incremented by 1 value each time, S1, S2, S3, and so on. But once in a while, it will be cleared to 0. So that is the reason we have to attach INR, CLR as an input to the sequence counter. It will be operated with the help of clock pulse, clock signals. That is why CLK is written over there. CLK for clock, CLR for clear operation, and INR for increment operation. Right? So at each time, its values are keep on incremented to generate the timing signals, because it deals with the clock. To generate the timing signals, how many timing signals will be generated with the help of sequence counter? 16. 4 inputs into 16 outputs, right? So it will be shown with the help of, again it will be fed with T naught to T15, right? So again, it will be given as an input to your combinational logic gate, right? So after that, some other inputs you will get, other inputs, and after this you will get the control signals, right? So the diagram which is drawn on the whiteboard, it represents hardwired control unit. Why it is called a hardwired control unit? Because we have used multiple hardware components like decoder, like instruction register, like sequence counter, like gates. So here we have a combinational logic gates. We have a multiple number of gates present in this circuit, right? It can be AND gate, it can be OR gate, it can be NOR gate, it can be XOR gate. Am I clear? Right? So I hope the concept is clear to you. What are the various inputs which are given to combinational logic gate? Right? Where you have 0 to 11. can see the diagram from your PPT. So one more input which is there, that is this bit, that is bit number 15, which will be given as an input to this combinational logic gate. So this bit will help you to identify the mode. If it's 0, which means you are working as a direct addressing code. If its value is equals to 1, you are working in indirect addressing code, right? So this is a simple diagram for hardware control unit. So in next diagram, which will help you to give the timing signals, right? So first of all, you can see that the first transition indicates the clock. The first transition indicates the clock. So here, because CLK is attached to the SC, SC is the sequence counter, right? So the first transition that is represented with clock. So here you have the clock. This is represented with the T node, which will be the first output of the SC T node signal, right? After that, again you have T1, then you have T2, then you have T3, T4, T5, and so on. This is your clock. T3, T4, T5, and so on. Right? So this is your CLK. Whereas T node, T1, T2, T3, T4, and so on up to these are your 16 timing signals which will be generated from the sequence counter. Right? So next we have represented with T node. How you can represent here? You can find that T node signal is in high position at this point only, and at other points it will be taken as a 0, right? So T node is achieving one value at this point only, at this interval only, right? Similarly for T1, your high transition will be achieved at this point, and for others it will be low. So this is your T node area, this is your T1 area, right? Similarly for T2, here you will get T node high and so on. I hope the concept is clear. Similarly, you can represent it up to T4, right? So you can see the diagram which is shown in front of you in the form of PPT. So here the concept is, assumption is there at time T4, SC is clear to 0 if decoder output D3 is active. So what we have to do? So here you can see that initially the value of sequence counter is clear. So that is why it is shown with the help of 0, right? SC, this lower signal is for SC and this is for clear. So we have taken SC to 0 over here. After that, the SC is keeps on incremented, right? So here SC is incremented to give you T node signal. here second time SE is incremented to give you T1, T2, again incremented here, again SE is clear to 0. So when SE is clear to 0, when D3 is active. So here you can see that D3 is active, right? D3 and T4. So this is your T4 signal. So SE is clear to 0 when the value of D3 and T4 is high. So this is the assumption which we have taken into the consideration, right? So after this, the value of SC is clear to 0. So this is the timing and control regarding to hardwired control unit, right? Next we have terminology. So first of all, the definition of microprogram is there. So program stored in memory that generates all the control signals required to execute the instruction set correctly, right? So a microprogram consists of micro instructions. Next we have micro instruction. It contains a control word and a sequencing word. Control word is defined as all the control information required for one clock cycle. Then we have sequencing word, information needed to decide the next micro instruction address. This is called sequencing word, right? So micro instruction is also defined as vocabulary to write a micro program, right? So micro instruction is defined as it is a vocabulary to write a micro program. Next we have control memory. So a storage in the micro program control unit to store the micro program, right? So control memory is that thing which is used as a storage in microprogrammed CU to store the micro programs, right? So all your micro programs will be written in case of microprogrammed control units. So the control information is stored in control memory. The control memory is programmed to initiate the required sequence of micro operations. Any changes or modifications can be done by updating the micro program in the control memory. If you remember, we have used many hardware circuits in case of hardwired CU. Hardwired CU. We have used flip-flops, we have used decoders, we have used sequence counters. So these are your hardware components. Flip-flops, logic gates, all are used in combinational circuits, combinational logic gates, right? So if you need any changes, you need to change the flip-flop, you need to do some changes in the decoder, you need to do the changes in the wires of sequence counter, right? So this is your hardwired CU. If we are talking about microprogrammed CU, you need to change the microprogram only. Understand the concept. You don't need to change any wire, you don't need to change any component, you don't need to change anything regarding to the hardware circuit. You just need to change the program. You just need to change some, you just need to make some changes in your program so that your selected micro program control unit will be changed according to your needs, right? So here you can see the diagram which is related to microprogrammed CU. So here again you have the instruction register, you have the decoder, you have the sequencing logic, and we have a special register which is called CAR. CAR stands for control address register. Then you have the control memory where all the microprogrammed instructions are stored, where all your information related to your microprogram will be stored. It is called control memory. One more register is used which is called CBR, control buffer register. So let me clear you, let me discuss in detail in a few while, right? One more decoder is used, right, which will help in the generation of control signals within the CPU and control signals to the system bus, right? So here sequencing logic will help you to give the next address control. So first of all, control memory. So micro instructions are stored in the control memory. Then we have control address register, address of next instruction. After reading the first instruction from the instruction register, control address register will be serving the purpose of address of next instruction, right? So the control address register will be taking the address of next instruction from the sequencing logic, right? So control buffer register, when a micro instruction is read from the control memory, when the instruction is read from the control memory, it is transferred to control buffer register. It also activates the control signals. Then we have a sequencing logic. So it loads the control address register and activates the read signal. Then we have decoder. So two decoders are used over here, number 1 and number 2. First decoder translates the operation code from the instruction register to the control address register. So this decoder will translate the operation code which will be present in the instruction register, right, to the control address register. This is used for horizontal micro instructions. So the second decoder translates the code into the control signals. So this is the second decoder which will be converting the code into the control signals. And this is used for vertical micro instruction. Remember these two differences. The first decoder is used for horizontal micro instructions and the lower decoder is used for vertical micro instruction, right? So to execute an instruction, the sequencing logic, this is your sequencing logic, activates the read signal for the control memory. So sequencing logic activates the read signal for the control memory, right? Again, it will, first of all, it will give the address of first instruction which will be loaded from instruction register into the decoder and from the decoder to the control address register, right? So the word whose address is specified in CAR is read into the CBR. So the address which is given to the control address register. So here you are getting the address. Only that word is read from the control memory and that word is given to the control buffer register, right? The word which is present at the address which is given by the sequencing logic to the control address register and from the control address register it will be given to the control memory, right? That word is read and it will be given to control buffer register, right? So the contents of control buffer register activate the control signals and generate the address information for next address information for the sequencing logic. So when the control signals of this word has been generated, the decoder will intimate for next address control, right? Because here you are getting the first word and its corresponding control signals have been generated by the decoder. After this, the next word will be fetched, and for next word you will need the next address. So the sequential logic loads a new address into the car based on the next address information from the CBR and the ALU flags, right? So here you can see the comparison between hardwired and microprogrammed CU. These differences are very, very important from the examination point of view as well. So first of all, the factor, the attribute which is called speed. So hardwired CU is fast, microprogrammed CU is slower. Second one is cost of implementation, because lot of hardware components are involved in hardwired CU. That is why its cost is more. And as comparison in microprogrammed CU, the cost is cheaper. Flexibility, the next third attribute, flexibility. So hardwired CU is not flexible, difficult to modify for new instructions. This is why, because we need to change in wirings, you need to change your circuitry if you have any error. And in case of microprogrammed CU, it is flexible. New instructions can be easily added because of the changes in microprogram only. Next, ability to handle complex instructions. So in case of hardwired CU, it will be difficult. And in case of microprogrammed CU, they are much easier to handle. Decoding. In case of hardwired CU, the decoding is complex, right? And in case of microprogrammed CU, it is easier. Applications. So hardwired CU's applications is RISC microprocessor. We will be covering RISC and CISC microprocessor in next chapter, right? So the application of microprogrammed CU is CISC microprocessor. Then instruction set size is small for hardwired and large for microprogrammed CU. In case of hardwired CU, there is no concept of control memory. That is why we have written absent. But in case of microprogrammed CU, your micro instructions, your microprogram is stored in control memory. That is why we have written present over here. Last attribute is control area function. So implemented in hardware. In case of hardwired CU, implemented in software in case of microprogrammed CU. So these are the differences between hardwired and microprogrammed CU. So the new topic is instruction cycle and memory reference instruction. So objectives, after going through this topic, you should be able to know the instruction cycle and its flow chart, determine the type of instruction, right? Then you should be able to understand the different categories of memory reference instructions. So first of all, what do you mean by instruction cycle, right? So the program is executed in the computer by going through a cycle for each instruction. This thing is called instruction cycle. This is the definition of instruction cycle, right? I'm repeating again. The program is executed in computer by going through a cycle for each instruction. So in a basic computer, a machine instruction is executed in the following cycle. So first of all, fetch an instruction from the memory, right? Your instruction will be fetched from the memory. This is the step one. Then step two, it is decoded, right? The instruction will be decoded. So the step becomes decode the instruction. Next, read the effective address from the memory. If the instruction has an indirect address, you need to read the effective address, right? Then that instruction will be executed. So these are the four basic steps for the instruction. This is called instruction cycle, right? So after an instruction is executed, the cycle starts again at step one for the next instruction, right? When your first instruction will be executed, right? So first instruction will be going through the four phases. The first phase is fetch, then decode, then read effective address, then execute. After that, the second instruction will be going through again these four cycles. Again, going through these four steps, or you can say that these four phases. Then similarly for third instruction, fourth instruction, and so on. Every instruction has to pass through this instruction cycle, right? So note, every different processor has its own different instruction cycle, right? So every processor, let's suppose nowadays we are using i3, i5, i7 processor, right? So it may be possible for i3, the instruction cycle is having only two phases, right? For i5, it is having four instruction cycles. For i7, it is having six phases, right? That is why it is written in the form of note. Every different processor has its own different instruction cycle, right? When you are writing fetch, then decode, then read EA, and then execute. So all these four phases will constitute one instruction cycle, right? Every instruction has to pass through this cycle. After then, the second instruction will be executed, and then the third instruction will be processed and executed, and so on. So here you can see the diagram for fetch and decode. First two phases of instruction cycle, that is your fetch. What does fetch and decode mean? So here you can see that timing signal T node. First of all, the program counter, it will give the address of first instruction to the address register, right? Where T node is equals to 1. So you know that the value which is placed in common bus system for program counter is 2. Right? That is the reason here you can see that S node, S1 and S2 is equals to 0, 1, 0. So this is the binary equivalent of 2. Right? So at T node, the address of first instruction will be loaded from program counter to the address register. Because the address register, which is of 12 bits, only this register deals with the addresses of various memory locations, right? So next we have T1, right? So at T1, the instruction which is present, at this memory location, it will be loaded into IR. So IR is the address register which stores the instruction from the memory, which is just read from the address register, right? And at the same time, the value of program counter, it becomes PC plus 1, so that to load the address of next instruction, because the instruction which is present at 0th location, its address will be given to AR, and that instruction will be transferred to the IR. After that, the first location instruction will be read out, and for this you need to increment the value of program count, right? So this will be done by T1 is equals to 0, and now here you are reading the memory address, and for memory you have which decimal value? 7. You remember in common bus system, your memory is placed at the very first position, and the number 7 is dealing with memory, right? So here the value of S0, S1 and S2 is equals to 111, because 111 is the binary equivalent of 7, right? So first T0 and T1 will give you fetch. This thing is called fetch. Fetch the instruction. Then again you need to decode it. And for decoding, we have T2, right? So here you can see that in case of your bit number 0 to 11, it will be given to AR, that is your address. So IR bit 0 to 11, it will be dealing with address, so it will be decoded to AR, that is your address register, right? After that, the bit number 12 to 14, the bit number 12 to 14, right, of IR, it will be decoded. It will be decoded to D0 to D7. We have just seen in hardwired organization, right? Your operation codes bits, bit number 12, 13 and 14, it will be decoded into 8 operation decoder signals, right? And the bit number 15, it will be sent to bit 15th of IR will be sent to I, right? So this is your T2. This is called decode phase. So fetch and decode. So you can see in the blow diagram how the T0, T1 and T2 is achieved. Let me explain it once again. Here you can see that T0. So T0 is attached to AR. T0 is attached to AR only, because AR is receiving the input, right? So first of all, PC is placing the contents. PC is placing the contents with the help of this signal. So any register which wants to write the data onto the bus, it will write the data with the help of these signals. So PC will be placing the data onto the bus by enabling the selection lines to 0, 1, 0. So PC will be putting the data onto the common bus. Now the data is present in the common bus and AR wants to read that particular data. So how AR will be reading the data? By enabling the load input. So this load input is connected to T node, right? So this is your first T node. After this T1, at T1, so first of all, M of AR. So memory will be read. So here the memory will be read. So it is here you can see that T1 is attached to memory and T1 is attached to PC and T1 is attached to IR, right? IR, memory and PC. That is why T1 is attached to three things. The first one is memory, the second one is PC, and the third one is IR. So first of all, the contents of memory will be read, but the bus is written, right? So it will be done with the help of S node, S1, S2, 111. So the contents of memory given to the this thing, right? So this is your this step. After that, and the address will be given by AR register. The address will be given by AR register. After that, the contents of memory is placed onto the common bus. Now you have to read the contents of bus, but the operation write will be performed onto the memory unit if it is required. But here IR has to read. So how IR can read? By enabling the load input, right? IR will read the data from the common bus by enabling the load input. And after that, the value of PC will be incremented by 1 so that the next address will be loaded to the AR, right? So this is the diagram which will constitute the fetch and decode phase. So next we have determine the type of instruction. So how you will be able to know that my instruction is memory reference instruction or register reference instruction, right? So first of all, at starting position, your value of SA is 0, right? You remember this thing, we have made it clear to 0 in case of hardwired, right? So I hope you have remembered this point. At last, when we have covered the timing and control diagram, here we have seen that this is CLR and this is your SC, and initially this thing is 0. That is why initially SC is clear to 0 always, right? So after this, the T node is appeared, but T node signal will be triggered. So there is your T node. So at T node, the contents of program counter will be transferred to AR. After that, at T1, the contents of AR, the instruction which is present at the desired memory location will be transferred to instruction register, and at the same time, the value of PC will be incremented by 1. So it will be covered at T1. Next, at T2, the decode operation will be performed, right? The decode operation will be performed at T2. So now, which bit will be able to help you that whether you are going to perform the memory reference operation and the register reference operation. Let me make you clear this point. So if you remember your instruction formats, we have covered three instruction formats. First is memory reference. The second is register reference, and the third one is IO, input slash output reference instruction, right? And what is the main difference between these three instruction references? In case of memory reference, your operation code is 000210. That is, the value will be equal to 0 to 6. That means that the 7 value is not achieved in case of memory reference instruction, right? In case of register reference instruction, operation code's value is 111. That is, the bit D7 is achieved, and the value of I is equals to 0 in case of register reference instructions. Whereas in case of input output reference instructions, again your operation code's value is 111, which means that again D7 is achieved, bit D7 is achieved, and the value of I is 1. I hope this concept is clear to all of you, right? This thing we have covered in 2 lectures back, right? So according to this, you can see that whenever D7 is equals to 0, whenever D7 is equals to 0, here is your D7, it means your memory reference operations are, your memory reference instructions are going to perform. So you can see this in case of right hand side, right? So D7 is equals to 0. This means memory reference is instructions. When the value of D7 is equals to 1, either register reference or IO, right? So let me discuss first of all memory reference. So here you can refer your memory in 2 ways. So again, the I bit will be 0 for direct, and here you have nothing to process, right? You need not to fetch one more memory location. That is why here it has been written nothing, and it will be doing at T3. And if I is equals to 1, it means you need to refer the memory one more time. So that is why here it has been written AR goes to M of AR goes to AR. And after this, execute the memory reference instruction, and SC is going to be clear so that the next instruction will be executed. I hope this thing is clear to everyone, right? Am I clear? After this, D7. Now when the value of I is equals to 0, so when the value of I is equals to 0, register reference instructions will be executed. When the value of I is equals to 1, input output instructions are executed, right? So when here you can see on left hand side, when value of I is equals to 0, execute register reference instruction and make the SC clear to 0 so that next instruction will be executed. Similarly, I is equals to 1 and execute input output instruction. SC is going to be 0 so that the next instruction will be executed and you will get the T4 signal. Sorry, T1 signal again, T1, because you are clearing the SC. So here you can see that D-7 so D7 dash, right? After that, T3 colon AR goes to M of AR. So here it means that T3 is equals to, when T3 signal is activated and the value of I is equals to 1. The value of I is equal, so this is equals to 1 and this is equals to 0. So in this case, your indirect addressing mode is achieved and memory reference instruction will be executed in the form of indirect addressing mode, right? When D7 bit is dash and I dash T3. So when the value of I is equals to 0, so when the value of I is equals to 0, it is your direct. And in case of direct addressing mode, you don't need to refer your memory second time. Here we are referring the memory second time, that is why we have written this. Here we don't need to refer the memory second time, that is the reason we have written nothing over here, right? After that, so when the value of D7 is 1, so you don't need to write dash over here, and but you need to write I dash and T3. So this means that D7 is activated, that is the operation code's value is 111, but the value of I is equals to 0. This means register reference instruction. This is your register reference instruction, right? Again, the second thing, when the value of D7 is equals to 1 and the value of I is not dash, this is your I is equals to 1 and you have T3. It means that your input output instruction will be executed. That's it. IO instruction will be executed. I hope the flow chart is clear to everyone. I hope the flow chart is clear to everyone.
Yes, sir.
So next we have register reference instructions. So which will be executed when the value of D7 is equals to 1 and I is equals to 0, right? So for register reference instruction, we are using B node to B11 of IR. Remember this thing, right? B node to B11. So these are your register reference instructions. CLA, which means that you have to clear the accumulator. CLE, you need to clear the end carry. CMA, complement accumulator. So accumulator's value will be complemented and it will be stored to the accumulator again. So remember one thing, you need to make the sequence counter clear before the start of these instructions, right? So next we have CME, end carry will be cleared, end carry will be complemented, sorry, and the result will be stored into E. Similarly, we have CIR. CIR means right circular shift. CIL means left circular shift, right? Then you have INC, increment. Then you have SPA and SNA, SZA, SZE. You just need to remember these names under register reference instructions, right? So next we have memory reference instructions. So here you can see that D node to D6 bits will be used for memory reference instructions. So that is the reason we haven't achieved D7 over here, right? That is the reason we have written D7 to 0. So for add D node, for add D1, this is your LDA, load accumulator D2. Then you have STA. STA means store accumulator, D3 will be used. BUN, branch unconditionally, D4 will be used. BSA, branch and save return address, branch and save return address. D5, ISZ, right? So we will be covering all these discussions in the next lecture, right? ISZ stands for increment and skip F0, right? So this is done for today.